In this video, I want to talk about cobwebbing, which is a really cool tool for analyzing dynamical systems in discrete time. We're going to look at a poverty trap model that we talked about in lecture this week. So let's get going. Hopefully I can share my screen without too much trouble. It's sometimes a little dicey. Nope. All right, good. All right, so what we're going to do is we're going to plot the wealth at time t plus 1. So wealth at time t plus 1 against the wealth at time t. And in order for there to be an equilibrium, the wealth at time t plus 1 has to equal the wealth at time t, right? You're staying constant, you're in an equilibrium. And so we can draw in a line of equality. We can just label that as the equilibrium where w of t plus 1 equals w of t. All right, now we'll draw our poverty trap model. As you may remember, it's a convex function down here. It crosses at some point kind of in the middle. And then it's a concave function here. We come back to the line of equality there. It should be pretty clear that this S-shaped function has 3 equilibria, right? Where w sub t plus 1 equals w sub t, where you're staying steady. There's a terrible equilibrium, you're destitute equilibrium, right? You've got zero wealth there and you're staying there. You've got this interior one, kind of right in the middle, and then you've got this good one at the top. And so our question is, suppose we start from a particular starting wealth, for example, start right here. What happens to us as we move forward in time? What happens to our wealth as we move forward in time? Well, how do we figure that out? The first thing we do is we draw a line up to our curve. And what is the curve? The curve relates our wealth at time t plus 1 to our wealth at time t, right? So in order to find out what our wealth will be at the next time interval, we just have to go over to the y-axis. That's what our function is telling us. And you can see that there's a, that's what our level is going to be, so that we can actually label that w sub 1. Now, this is a slightly awkward thing. We have to sort of measure how high that is and then rotate down. You can't see what I'm doing with my fingers, but I'm trying to measure it. Right, and this is where our w sub 1 is, where we start for the next iteration. Okay, we go up there. That's pretty bad news, right? We've taken a big jump downwards, and we go over to the y-axis, and we've got w sub 2, and then we can put our w sub 2 there, and it shouldn't take a whole lot of imagination to realize where this is going, right? You end up, when you start here below the middle equilibrium, you're going to end up in that destitution equilibrium. All right, but it's a little awkward having to sort of gauge how far up the y-axis you are, and then rotate it over to the x-axis for your next point, right? Let's just, before we move on to the cobwebbing way of doing this, which is much easier, and it's quite intuitive. Let's do an initial condition that's on this side of the equilibrium, of the middle equilibrium. So we'll call that green w sub 0. And we go up to the function and then over to the y-axis. And then I'll try my best to measure. We go to about, that's w sub 1. This is w1. We go up again. Try to keep these somewhat straight. And so our w2 will be here. And that So W2 is here. We go up. And you can see, oh, yep, all the way to the function, not to the line of equality. We come over here, that's our W3. And again, it's not going to take a whole lot of imagination to recognize that we're eventually going to hit that good equilibrium, the one that we want, the wealthy equilibrium. But you can see it's particularly when you're drawing it by hand, it's a rather inexact way of understanding what's going on with the model. Let's do a new and improved way, and this is what cobwebbing is. So I'll redraw the axes. W sub t, W sub t plus 1, draw on the line of equality again. Draw in the poverty trap model. Make sure the line of equality gets all the way up there. All right, so what are we going to do? So let's think about what that line of equality is telling us. Here, as we go to the function from our W sub naught and then over to the y-axis, note that we pass through the line of equality there. Right? It has the same y value, y-axis value, as going all the way over to the axis itself. All right, and so what we're going to do is, rather than going all the way over to the axis, we're going to have our next starting point being here on our line of equality. Now, the one thing that's different, of course, is that we're not going to be going up to, we're not necessarily going to be going up to the function, right? Here, the line of equality is above the function, right? So we'll go over to the clean one, put in W sub 0. We'll go up to the function and then over to the line of equality. And now, because the line of equality, this equilibrium line, is above the function, we then have to go down back to the function, right? So that becomes our W sub 1. All right. Now we go back to the line of equality from the function. We go over to there. There's our W sub 2. Back down to the function. All right. Back over to the line of equality. That's our W sub 3. Function. Line of equality. We're in the bad place. It's much easier, and it looks nicer. It gives you get more accurate dynamics, like your increments are easier to see, and you can actually, when you do this particularly for more exotic models, you can actually get a sense of what the dynamics are. Here, we'll start above the interior equilibrium. Maybe not. We will go up. It's always harder to draw to the high equilibrium. So now our function is above the line of equality. So we go across, and there's our W sub 1. We go up because the function is above the line of equality now. We go over. There's our W sub 2. Up and over, and lo and behold, we're in the good equilibrium. That's cobwebbing in a nutshell. We call it cobwebbing because, we create what can look like, particularly for hump-shaped, like a recruitment curve. What you can get is cycles, and they look like a spider web. Really super powerful tool. Great for, and this is in discrete time, so it only works for discrete time systems, but a lot of the things that we are interested in, population models, are often rendered in discrete time. The poverty trap is obviously another one. Basically, all the models that Halling 1973 talks about, right, are all done in discrete time like this. So this is a super powerful technique that you can add to your arsenal of tools for analyzing dynamical systems and understanding resilience. Hope you found this helpful. See you soon.